Hello everyone, I'm Tom Hudson. I'm a geek, I guess, from Bradford. I work as a solutions architect at Skybeck Gaming in Leeds. And I like to fiddle with computers, so I would like to fiddle a bit with a computer this evening. So, let's build a virtual machine. But I guess to start off with, what is a virtual machine? So, without trying to be at risk of sounding a bit stupid, it's kind of like a real machine, but virtual. So I guess the one way to think about it is it's like a pretend computer. So you have a CPU and you've got memory and all this sort of thing in the real physical machine, and then a virtual one is just the same thing but simulated in code. So when you write code in a high-level language like PHP or Java or Ruby or Go, actually, not Go, that's a bad example. You might write something like print 2 plus 3. But the thing is, the CPU can't really do anything with that. So in a language that runs on a virtual machine, it first gets converted into what are called opcodes, which look a bit like this. That's actually just numbers, and then a VM runs the numbers to arrive at an output, does stuff with them. So when you haven't got a VM, a real CPU does that, in this case. So the method by which the code's executed is this loop. It's called the fetch, decode, execute cycle. So you fetch a number, you have a lookup table to say, when I've got this number, what do I do? That's your decode. And then your execute is you do that thing that your lookup table told you to do. So as an example, we have this original program that I had earlier on, which was 2 plus 3, and print it. So we have this operation at the top here that says push 2. So a virtual machine has a few things. You've got code that's in there. You've got a thing called a stack, which is a bit of last in, first out memory that you can put things on and take them off and push and pop. You have a thing called a program counter, which is a thing that says, this is where I am in my code currently. So after every instruction, that gets incremented. So this chappy on the left here is our program counter. And then to be able to use the stack, you have a thing called a stack pointer. So to start off with, you've got nothing on your stack. You push something onto it. The sheepy on the right points at it. You push another thing, he moves up again. So we have this first operation, push 2. And all that does is push the number 2 onto the stack. Pretty simple. We move down a line, so the program counter has moved down. And so push 3. So we push 3 onto the stack. Now, we move to the next one. We have this add operation. And the stack on the right-hand side has changed quite a bit. So the stack point has moved, and that 2 at the bottom has changed to a 5. We'll run over wide in just a sec. But then when we jump to the last operation, we print, and we have our output sheet at the bottom who prints 5 on, I guess it's an easel. So I mentioned the stack changed quite a lot between this add and push operation. So it's the add that changed things. So what that add operation actually did was we started off and said, right, we've got a 3 on the stack, and the stack pointer is pointing at that. So we pop the 3 off the stack, so we're now pointing at the 2. So we know we're going to do 3 plus something. Then we do the same again for the 2, so we know it's 3 plus 2. We know the answer's 5, so we push that answer back onto the stack. So we end up with 5 at the bottom. So why would you need a VM? One of the answers is that compilers are actually really difficult to write. So there's a bunch of different CPUs and things like that. And if you're distributing software, if you want to send out binaries rather than source code, you need one binary for every different CPU architecture that exists. Right. So let's make one, which will hopefully sort of try and demystify them a bit. A lot of you might read about, say, the JVM or the, does Ruby call it VM, the RVM? Yeah. There's the PHP VM. There's a whole bunch of them. But you can try and demystify it a bit. So I had originally said that I was going to do this in either PHP or Go and put it up to the vote. A bunch of people I've talked to have said that they like it in Go. It's kind of what I'm leaning towards. So if you would like me to code in PHP, can you give us a shout? Okay, and in Go? Okay, let's do it in Go. Fine. Right. So we are going to make a directory, call it Stac VM. Okay, so text size wise, let's see how we're doing for this. So we're just going to have, we are in package main. So how's that text wise? Can people read that at the back? Yeah? Oh, lovely. So for those of you who don't know Go, don't worry, I'm not going to be using any sort of really advanced Go concepts or anything like that. It's relatively C-like in its syntax. I'll try and explain anything unusual as I go along. Right. So, ordinarily, you would have some kind of compiler which compiles a high-level language down into these opcodes for execution by the VM. But we're going to kind of skip that, and we're going to write sort of pseudo-assembly. In order to do that and make that a little bit easier, we're going to need some constants. So we need something to represent the push. And one of the first sort of little Go-isms that's in there is this thing called iota, which is kind of, it's like a little auto-increment thing. So when you have a const block like this, you can say this constant equals iota, and then in every subsequent thing you add in there, it adds 1. So we're also going to have another thing here. Print, push, add, print, halt. So in this case, push is equal to 1, add is equal to 2, print is equal to 3, halt is equal to 4. It doesn't actually matter so much what they equal. And we need some code. So we will stick with the program that we first wrote. So we're going to have, it's just an array of integers, or what Go calls a slice. So we are going to say push 2, push 3. Add them together, print them, and we're going to say halt as well. So I realize I didn't have halt on my slides, but it's relatively important because otherwise we end up in an infinite loop. So this program does not do anything, but it does complain that I've declared code and not used it, which is fine. So we need a VM. So we're going to have a type of VM, which is a struct. And I said that VMs have a few different things. One of the things they have is code, which is an array of integers in our case. They also have a program counter, which we're going to abbreviate to PC, because we have to use it quite a lot, which is just an integer. The other thing they have is a stack, which is also an array of integers. And in order to see where we are in the stack, we also need a stack pointer, which is an integer. Lovely. So that's kind of all the data that we need in our VM. But we need to make it do something. So we are going to have a method on our struct called run. And that's going to accept some code, which we'll call C, which is an array of integers. So we can then say, I want a new VM. It's actually a pointer to a VM. And then we want to call run with this code. Okay, so we're still not doing anything, but we should have no syntax errors, which is great. So at this point, I am going to set something going, a watch, on this right-hand side, so I'm not jumping between the execution and the code quite so much. So we want to say go build and run stack VM, which should, so the code's kind of running every 2 seconds in that right-hand column. But at the moment, there's no output. From time to time, you'll see syntax errors, that kind of thing. I'm probably going to make mistakes, so if you spot an obvious one, please do shout out. Okay, so we have this run function, and we can actually start getting to the meat of this thing now. So first we need to do some initialization. So we have our stack needs to be something. In our case, it's an array of integers, so we just need to, whoops, a daisy, not replace, fool. We just need to allocate that. And our stack pointer, for reasons we will go into, needs to be initialized to -1. And our program counter, we're going to initialize to 0. And we've got one more thing we've missed, which is we need to actually set the code. So that's all initialization stuff. So where all the actual logic thing happens is an infinite loop. So we have that fetch, decode, execute cycle. So the first thing we need to do is fetch. So what we need to do is say the operation, or the opcode that we're looking for is wherever we are in the code at the current program counter. So program counter is 0. Code is just an array of all of the codes that we're passing into the virtual machine. So op is whatever the first code is, which is fine. And then we want to increment the program counter. So at the moment, this will infinite loop, so I'm just going to kill the thing on the right-hand side before my laptop starts to die. So we then need to decode it, which we will do with a switch statement. So our operand can be one of many things, but one of the things it can be is a halt. What's going on there? I think my indentation's gone a bit weird. Oh well. Okay, it's halt. We want to return, so we don't get an infinite loop. That would be bad. So we should be able to run this on this side. Lovely. So we're still not doing anything. We're still not getting output on the right-hand side. So we have a few different possible opcodes. So we can push something, we can add some stuff, or we can print some stuff. And hopefully, so at the moment, all it's doing is going through all of the opcodes, and it's doing absolutely nothing until it gets to the end here, where there's a halt, and it stops, which is immensely boring. So let's make it do something. So the first thing we want to do is implement this push opcode. So what you need to do for a push is take the next thing in the code, our constant, and we want to push it onto the stack. So our value, I guess you could call it, is the next thing in the code, which is where our program counter is. And we then need to increment our program counter to say, this thing wasn't an opcode, it was a constant, we've skipped over it. And then we need to put it on the stack. So we need to increment the stack pointer, and then we need to say the stack pointer, where the stack pointer currently is the value. File declared not used. And the errors have gone away, which is always nice, but it's still not doing anything. It will do something, I promise. Right. So then we've got our add operation. So you might remember from the slides, when we do an add, we take the top two things off the stack, we add them together, and then we push the result onto the stack. So we're going to have A, which is the first thing, the thing on the top of the stack. So to get that, we need to say the stack pointer, stack of the stack pointer, so that's the thing on the top. Decrement the stack pointer, and then we do the same thing again, but we call it B. B not declared, that's fine. Then we need to add them together and push the result onto the stack. So even though we've just decremented it, we need to push it back up again, and then say the stack pointer, is equal to A plus B. Hopefully no errors on the right-hand side, but we're still not displaying anything. So we have one more thing to add in before we have some output. And with a bit of luck, when I've written this section, the right-hand side, we should see 5, which is very exciting. I realize this is possibly the most complicated way you could do 3 plus 2. Right. So what are we going to print? It's the thing that's on the top of the stack. So we want to get our value to print, which is whatever's on the top of the stack. So stack point, vstack of stack pointer. And then we will do format print line of that value In the meantime, because we popped it off, we will decrement the stack pointer. Include that package. And 5! Hooray! I cannot believe that worked. Right. So, at the moment, we're just outputting 5, which is a bit naff. It would be nice if we could kind of see what was going on. So, what we're going to do is add a new method onto this VM struct called trace. And at the moment, it's not going to do much. We're going to call it right here, trace. Okay, let's make it do something. So what we'd really like to do is, at every run of the fetch, decode, execute cycle, is see what's actually going on. So we want to know a few things. So we want to know where we currently are, which is the, not stack pointer, that's silly, which is just the program counter, so the address of where we are. We'd quite like to know what our current operation is, which is the code of the program counter. So just wherever we currently are in the code, that's our current operation. Now, we'd quite like to know what our arguments are as well, but we're kind of missing some metadata here. So each instruction takes a variable number of arguments. A push takes 1 argument, add doesn't take any arguments. So we need to go back and define that and say, I'm going to have, in this case, what would it be? A map of integers to something called operations. Ops, but we need to first define that. So we will have a type op, which is a struct, which is just something which has a name, which is a string, and it's going to have a number of arguments, which is just an integer. And we'll have an array of those, well, sorry, a map of those, where we say push is an op, and it has the name push, and it has 1 argument. Relatively simple. So we need to do that for each thing. Whoops, a daisy. So this one's called add, and it has, not 9, honestly, has 0 arguments. Print is called print, also has 0 arguments. And then we have halt, which is called halt, and also has 0 arguments. So we hop back to our trace function. We can now do a lookup on that ops array. So we have, instead of just a number, we have a struct which gives us some metadata about that. And apparently I've got a syntax error on line 17. I've missed an equals, which is frankly ridiculous. Syntax error, that's fine. Okay. So we have our address, we have our operand. Let's start printing some of this stuff out so we can kind of see what's going on. So we want to print f, and we're going to have, I keep putting semicolons in because I've been writing VMs in Go and PHP alternately for about the past 2 weeks. So if I start putting PHP syntax stuff in, please shout out and tell me. So we're going to have the address, which is an integer. And let's throw that in there. And then we're going to have the name of the op, which is a string. Then we're going to have the arguments, which is the special, Go has a placeholder to say this is a value, which is v. And then we're going to have the stack in the end, probably separated by a tab character. So if we throw in the address and the op.name, ooh, the output's changed. We'll just put this text size down a little bit. Apparently we're missing some stuff, but we will fix it, I promise. We'll put that in the right place. A new line character on the end. So we've got the current address, we've got the operand, and we now want our argument list, which is going to be in our code, so somewhere in vcode. And Go has this nice little bit of syntax where you can get a slice of an array just by using this colon syntax. So it's going to be somewhere ahead of our current program counter, up to the number of arguments plus 1, I think. We'll soon find out how right I've got it, or how wrong I've got it. So we have the name, we have the arguments, and then we want the stack as well. However, we don't want the full stack, we want just the bit of stack that's in use in this case. So it's going to be another slice, and we're going to go from 0 to the stack pointer plus 1. And we have a runtime panic. And we are out of range on something in the trace. If anyone wants to help out, that would be lovely. So push to slice out of bounds. Oh no. So we're somewhere around line 35, which is 35 in the arguments. So, what I actually want is the program counter plus the number of args. That's plus 1. VP? V. Terribly sorry. It turns out, interestingly, writing the trace function is the most difficult thing about writing a VM, which is probably not the way it should be. But on the bright side, it's working. Sorry about that. So we can now actually see what the VM's doing. So we have our first operation instruction at address 0, which pushes 2 onto the stack. So the stack's this bit on the right-hand side here. So on the next line, you can see we've now got 2 on the stack. We then push 3, and 3 magically appears. We add them together, and we end up with 5. We print 5, and we halt, which is kind of nice. We can see what's happening, but there's still not really any logic going on. So what I'd like to do is add another instruction which provides us with a facility to do some kind of logic. So by shouting out, how many of you are absolutely bored witless and would not like me to do that? Okay, just one. If you find me afterwards, I will apologize to you in person. I've got some brownies. I'll give you a brownie. Okay, so we're going to add another instruction, which in this case is going to be slightly cryptically named. But what this is jump if less than. So we want an instruction which says, take the thing on the top of the stack, compare it to this number, and then if it's less than that number, we want to jump back to a different part of the program. So we need to define a name for it in here as well. Jump less than. And nice to be different, the jump less than instruction is going to take 2 arguments. So add it to our code so you can kind of see hopefully what it is. So what we're going to do is after the add instruction, we're going to say, if the thing on the top of the stack is less than 10, jump to address 2, where address 2 is this second push statement, which is currently going to break everything. And then we're going to fix it. So in the case of jump statement, so we have 2 arguments in this case. We have our thing we want to compare to, which is the next thing in the code, program counter. And we have an, oh dear, I think I've hit caps locks. So that is a tip for you. If you ever get really, really weird stuff happening in Vim, you've probably hit caps locks. Okay, so the address is the other thing, and we want to increment the program counter in between times because we're using those things. And we want to say, if the thing on the top of the stack pointer, is less than whatever that is, then we want to move the program counter to that address. And with a bit of luck, lovely, we have more output. And our final thing that we print is now 11, and not 3. Oh, not 5, sorry. So now we've got logic, which is great, because without it, you can't really do anything complicated. So if we follow the trace of the program from the start, we start off by pushing 2 and then 3, and we add them together. And then we compare the thing on the top of the stack, which is 5, to 10, and say, is it less than that? Which it is. So we jump back to address 2, and we repeat. Except now, this time, we're adding 3 to 5, and we end up with 8. And we do the comparison again. It's still less than 10, so we loop around again until we get 11. And then it's not less than 10. It's possibly the most profound thing in this talk, is 11 is not less than 10. And then we can print it at long last. And then we halt and stop. So real VMs have many, many more instructions than this. So they'll have just a regular jump. They'll have subroutines, which are unfortunately about as complex again to implement, and I don't want to bore you too much, but basically involved saving the current state of the whole virtual machine onto the stack, doing stuff, and then coming back again using that stored state from before. So if you want to make your own programming language, you might find yourself writing code like this, but I hope at the very least, when you hear things like the Java virtual machine or something, it's not, so it's complicated and it's big, but at its core, it's not really any different from this. It's just a really simple state machine with a couple of different kinds of memory attached to it and a really, really big switch statement. Thank you.